Oh. So you have two paired. You have president's heights and the opponent's heights. This is... This one doesn't have data, does it? It just... Let's see. The table below shows paired. Oh. Okay. So, open and stat crunch. Isn't that nice? So, if I want to do like a scatter plot, let's say, actually, I'll show you one of these anyway. Box plots. Let's pick the presence heights. And then, plot group for each column. Oh, maybe, I don't know. So anyway, let's try that. Okay. So this is called a box and whisker. So this right here is this going to be your median. So let's see. So that's, you know how to get the median, right? You just line them up. From smallest to biggest. Does anybody know what I'm talking about? Okay. Now, guess what these are? Why, these would be the extreme points, right? So when you see a stock market, you'll see a lot of times that at every 10-minute intervals, you'll see these box plots. Let's see if I can show you one. Let's see. Let me just bring it down here for a second. Oops. I'll get the hang of it. Actually, I'll just do another one of these. Oops. Oh my gosh. Let's see, do I want to do that? So that goes off. Okay. And then, how do I go? Let's see. Okay. That's right here. Okay. Let's see, stock market. Stock market. Let's see. Let me go. Let's look for box plots. Highs and lows. You see how each one of these is a box and whisker? This was the range from that period. So I've used quite a bit, the box and whisker. Let's see. Okay, so we're over here. All right, so that's how you do that. But we were asking here about, are these two related in some way? So we look for, what statistic are we looking for? What statistics tells me whether they're correlated or not? Not the mean, not the deviation, not the histogram. Yeah, correlation coefficient, right? So we go, well, let's look at the scatter plot first and see if we can see something. Okay, so I'm going to pick one, it doesn't really matter. Let's say the height and the opponents, right? Okay, and then I think that should do it. Let's see. All right. What does that look to you like? It looks kind of, well, it is a scatter plot, yeah. But does it look like maybe they're not tied together? I don't see a structure in there. What do you think? Here? Well, you want me to change the scatter order? Scatter plot. So you can make any one of these. this way. Is that what you mean? I'm comparing, to see if one is moving with the other. Oh. There's no relationship that I can see of unless, you see what I mean? Now, the coefficient itself, we go to stats, right? And then we go to summary statistics, and then you see correlation. Okay, now, so let's see. So that's height, or opponent's height, and then let's see. There. Okay. Now, there's this thing we're going to be calling, I don't know if you've read about it yet, called a p-value. Anybody? Okay. So, let's see. All right, so this is, remember this goes from -1 to 1. Yes or no? Yeah? And this is at 0.15, so there's a 15% correlation, which I'd say is not very good. But this right here, I don't know if I have this or not, is the p-value. And I'll show you how to read the p-value. It turns out, if you remember, we had a distribution of a correlation coefficient where it had like this region here, and then we had what they call these tests, or what we call critical values. And we're setting it at 95%. So on this side, you would have, like, let's say if this was the area under a curve, right here. Okay, and here. Okay, so this here is where we're going to reject. Okay, and then this is a confidence interval at 95%. So the area under the table, I mean, it's going to be 0.025. Do you see? Because that adds up to 5. It's the correlation coefficient. They're just setting it at 95%. So I just happen to know. So the area under this, right, actually measures, this area is 0.025, right? Because the total area is 0.5 in the tail, in the tails. So I look at this value here, and I say to myself, which is bigger? In other words, the area under the tail, which is 0.025, right? Or this, 0.57. So this is, I would say, a bigger number than that, wouldn't you? I would do this. That's an inequality. Okay? So what that means is that the p-value is hitting somewhere. If it were to hit somewhere here, it's going to be more than in the tail. It's going to be somewhere in this area. So the p-value might end up here. It doesn't tell us what it is. I mean, it tells us how much it is, but I can tell by the area that the p-value is going to be, 57. So it's way over here, like. So it doesn't look like this p-value would tell us, because this is the reject zone for us. Reject that there's a correlation. Okay? I put reject. Okay. So now, from now on, you're going to figure out what it is. So if you look at the question, let's see. Let me go back to the question. Let's see. Let's see. And question was it this one? Yeah. Let's see. So, no, there does not appear, there's no general pattern. Oh, okay. So, it looks something like this one, doesn't it? Or Or even that one. That looks like the same one turned on that side, doesn't it? That look more like that. No? Okay. Any questions on that? Here we got carbon monoxide and cigarettes. Let's take another one look here. Any questions on this? How to do the scatter graph? Okay, now. Okay, so since is between, okay, so look at this value again. Now, here's the R. That's not too strong, is it? So let's look at this. So let me clear that. Let's see. Okay, so assuming that this correlation has a distribution, like, in other words, it's a variable too, the correlation itself. So if it was something like, let's say, bell-like, do you remember what the area is under the curve? 100%, right? Remember we had the histogram, and you had different bends. Do you recall? I mean, you had to fit in one of those cells, right? So if you take that frequency divided by the total frequency, you have a probability. So, and what we want to talk about is being at the 95% confidence interval. Confidence interval. So what that means is that, from 100, you got 5% left. True? But if I'm using a two-tail, then I have to take the 5% divided by 2. So 0.025, right? And so too here. So we'll be finding these critical values here soon. But even without that, we can look at our p-value and then ask which one of these, which is bigger, this or that? If this is a bigger area, right? If this is a bigger area than that, that means that coefficient is falling somewhere in here, which is our reject zone. Reject that there is a correlation. All right, this we'll be doing a lot more of this and more intensive, but this is just right now a little taste of some hypothesis testing, really. So we're saying if the critical statistics come out to this, and I look to see whether, this is the accept. The accept, and the accept is the same for here, this area, and this area. If, suppose that this was smaller than 0.025, so let's say 0.021, right? So then I'd say, okay, in this case, the area under the curve is greater than the p-value. Do you see that? In which case, we'd be landing in here or over here, which means there appears to be a correlation with the 95% confidence interval. So in this guy, it says, since the coefficient R is between the critical values, remember these are the critical values? I was telling you. I'll tell you what the actual number. It's 1.95 plus and minus. I think it's 1.95 minus and 1.95 plus would be the actual values of the critical with 5%, with 2.5% in each side of the tail. Okay? So there is not sufficient evidence. Is that good? Yeah.
And how do you get the critical value again, that 0.576?
0.57. That 0.0576. That's given to you. I mean, you have to calculate the R. So let's see. Oh, here's the R right here. So that's 1.65. Now the critical values. Yeah, they're telling you point. Yeah, they're telling you. I thought it was 95%. Number of pairs in data. Oh, there's a 0.95. Remember, and I took 0.5. But the number of pairs here are how many? Well, there's at least 12, right? So now they're using 0.76, 0.576, right? Do you see why they're using this critical value? It's they're saying as the number of scatter points increase, the number of pairs, right, height of the opponent to the president's. Okay, so it's just saying that this area under the curve is getting right. It's getting what's getting bigger, isn't it? Well, it's getting bigger. Okay, let me draw it for you. So okay, so this here right here now, instead of so here I had 0.95, right? That left me 0.05, and this one, wow, this one here is 0.075, 0.570. So that's it's plus and minus 0.75, right? So this thing's centered around 0. So we have so. Let's see. This should be about right here. So this is hitting here and here. So you see what happened to the restriction and accepting range. So well, look at that. Compare it to your. Let's see. Okay. Well, that's the critical values. Okay, so now we got the coefficient. So anyway, they're telling you here, you're not calculating it, they're telling you what critical values to use based on the number of pairs. Okay, then we look to see where this thing falls in relationship to plus and minus that. So if I do like this, maybe it'll make it easier. Suppose I go like this, right? And I just find 0, for example. And I'm going to say that this is like plus 0.576, and this is minus 0.576, yeah? And so regardless, you can see here, because now I don't know, there's not giving me a p-value, is it? So what's happening in this case, my tails are over in here. So this area here is my accept. So that's reject. That's reject in here. If the correlation coefficient, was out in the tails, then you would accept. So the reason this number came in place is because we had more than 4. See? We have 4 pairs, we had 12 pairs. So it's throwing these critical values. So all you have to do is see where the critical value hits. If it hits in between, you're going to do a plus minus of each one of these. One's on the right hand of 0, one's on the left. So if the R is falling inside, but not at the tails, then we're rejecting that there's a correlation. And if you look at it, that's not much of a correlation. It's like, right? It's 16%. So, okay, let's take a look at that one. Let's try another one. Okay, now, it doesn't tell us how many are in the data set, does it? It says, so look at this R, it's 0.95. Right, and 0.956, you see that? So let's just do the, just right here. Look what I got. I have 0, right? And this is almost plus and minus 1. Okay, if that's the critical values, then I look to see where my R hits. Where's it hitting? Well, it's 0.956. So I would say it's just a hair over here, would you? So the right tail above the positive critical value, that's the right tail. Yes or no? I got a feeling no. Yes? Okay, so remember this was reject. So these two areas are accept. You'll be expert at this after a while, but this is just a taste of hypothesis testing. I don't know why they bring it in right now, but anyway, might as well cover it. You follow me? Now, that would be from here, but, oh. But it doesn't tell me how many pairs, so they picked this one. Okay. So all of you had this homework already done? It seems like you already know it. No? Oh, you're not doing it from the book? You're doing it from the book? Okay. So here we have volume of the brain. Supposedly the bigger the brain, maybe the smarter. Is there a correlation between brain size and IQ? Could be just hot air in the brain, right? May not be anything. But, so we got a p-value of 0.54. Let's see. Okay. So did they give us the p-value, right? Is 0.58. So it's close because it depends what they're using as the critical value. But if you're using this one, 0.95, right? So remember, I have to take, this is minus. So I know that the total area has to add up to 1, correct? So I have to figure out how much is left over on this end of the tail. Well, if I take 0.025, right, and then I add another 0.025, if you added this and this and this, right, so you should get 100%. Okay, so now look at the p-value. Now, does that hit to the right or left of that? Of this critical value. This is, I'm talking about area, 0.025. So now I'm asking, is that bigger or smaller? It's quite a bit bigger, isn't it? Well, it's if you want to change it into decimal, right, you're going to have 0.548. And I'm saying that that's bigger than 0.025. Or, as I say, I had the critical value. So this looks like it's going to hit on this side, right? If I'm going this way, the area, right? Or over here, maybe. We don't really know. But I do know it's in the reject zone, right? So there's our linear coefficient. That's the r squared. And so there is not sufficient evidence. Now, high, I think high just means, oh, look at this p-value. Actually, they're right on the same. What? Yeah, okay, so it says R. Okay, so the p-value is, it's a high number because it's way over here, you see? 0.54 is twice that. Any questions? Too easy? It's like I'm solving your math problem? Okay. Let's see. Okay, here we have a p-value again of 0.038. Okay, so the p-value indicates the probability of a linear correlation as extreme as 3.8. Would you agree that's not a strong correlation? So it's low. So now, if I was thinking of the curve, let's see, if I was doing this one, then, and I had the same idea where I had this tail here and this tail here. Okay, so this tail is like, well, I'm going to say minus 0.95 and 0.95, right? And I know that in this tail, by my calculation, 1.25. So now I'm comparing this, which is the area under the curve, to the p-value. And I ask which one's bigger. So what do we have? A p-value of 0.038. And I'm asking what's bigger, 0.038 or 0.025? Let's see, does it say how many? So this is bigger, isn't it? So I wonder if they're putting 0.025 in here. Let's see. Okay, so you could ask me. I don't know if that works. Does it open it up to the actual page? Does anybody know? That'd be cool, huh? But it's probably page 1. Oh, what the heck? I got a book right here. Let's see what they're using for the coefficient. Oh, you know what? I got to take roll too. Might as well get that out of the way. Said Carla. And then, oops. Carla, Mindy, Jesse. Shauna. I'm going to have that one down. Noah. Harry. Ruben. Uh-oh. Callie. Keisha. No, I just screwed that up. And then Precious, yeah, and then Sean. Alexander. Joseph. Sarah. Is Sarah here? Kira. Moxley. Huh? Oh, we can see, yeah. You think I'd get it by now. Braden. Okay, and then Austin's not here. Willard. And Wyatt. Okay. All right, so let's see here. Oh, I didn't even notice that. Okay. Yeah, let's see. Okay, that's perfect. It opens it up. Can't get much better than that. So you pick the axis. We run the correlation. I have to show you the correlation of waist and circumference. That's Appendix B. It's exercise 7. Okay. Waist and arm circumference. Waist and... Okay. Let's just show right here. Weight of pennies and years of production. Okay, there's R. Okay, so remember R is between -1 and 1. Right? Because you can have a negative slope or a positive slope. You know? So if you see R of 0.8, that's pretty good, right? As opposed to R of 0.028, that's pretty close to 0. What's it mean to be more negative? Well, if it's a bigger negative, that means it's tight, but the slope is going like this, negative. Yeah, that'd be positive. Okay? The slope, negative and positive. And we went over that. Okay. Here's the correlation coefficient, right? And here it gives you the critical values. Well, that's nice. It gave you a critical value of plus and minus 878. So, let's see. So 878. So you have something like this. So here's 0, right? And then we'd have a critical value of plus and minus 0.878, whatever, and then that's minus 0.873 positive, right? And okay. So if this is a two-tailed test, the p-value is 0.029. So if I had the area here, okay, so this is a two-tail is 0.29, right? So they're giving you a critical value here. Yeah, and then you can see where R falls in relationship to that. R is what? 0.059? About right here. And in this case, the p-value, well, I don't know if it's bigger or smaller. You see right here? The two-tailed is that's telling you how much is in the tail. How much area is in here? 0.29369, right? And let's compare that with the p-value. So the p-value is that, and let's compare it to where it would sit here, right? Okay, now, this is like 60% correlated. And now this will tell you whether to reject or accept. If in the tail you had 0.025, you can see you're in the reject area. But if you, so let's see. Oops. Okay, so these are the critical values. Like, I've been superimposing this distribution over it, like this. You see? And these are the critical values that, in this case, they gave it, right? True? Now, where does R fall in there? Well, I'm not comparing p-value right now. I'm just looking to see where my R statistic hits. Do you see it's hitting between the two critical values? And that means there's no correlation. Even though that's 60%. But with this kind of level of confidence, we still would reject that as any meaningful statistical value. Any questions? Is it too easy? So here's that thing you were talking about. This is how many paired values, and this will change your critical value. You see right there where it's 0.878? Well, that's 0.878 and minus 0.78. So they're saying that the number of paired is 5. I didn't actually see the data, so I don't know. Okay, interpreting the p-value. Okay, so the p-value on this problem was 0.294. Okay, so this one's R is 0.59. It says, okay, so here's only small values. Okay, so only small values of p, such as 0.05 or less, of 5% or less, suggests that the samples are not likely to occur by chance. That's good, right? So look at this. I'm trying to make sure you get this. So the p-value supports the conclusion that there is a linear. Now, the p-value is small, right? And the reason it's that is because if you look at just one tail and you have a critical value here, you know at 5% there's 0.025 even. And now I can compare that number to my p-value, which is this one. Do you see that? 0.05. So this one here is bigger than 0.025, isn't it? So there's a 5% chance of less. So my p-value, oh, that is 0.025. So the p-value is 0.025. So if you compared it with 5%, that's what they actually look like. They're putting the whole 5%. Let me check this. So you can see that this is, let's say in the tail end now, instead of 0.05, they put 0.5 like this. 0.05. So it's just about right in here. So if it's in this area over, we accept. Let's see if we can do some more of those. Oop. I'll get it. Okay. This is shoe print length and height. So let's take a look at it. I would say it's, you see it has a correlation value of 0.81. And it's positive, right? You see that's a positive slope? The line's positively sloped. This would be negatively sloped. And it's pretty high, right? And a p-value of 0. You know that's a lot smaller than what's in the tail area, right? Isn't it? I'm saying that if you have this graph, okay, you know how much area is in here. I mean, even if it's a little bit, that's 0. So this area in here, this area, you want to compare this area to this number and ask which one's bigger. Well, this is anything bigger than 0 is going to be bigger, right? So I'm saying that the test statistic is hitting in here somewhere. And if you recall, that's an accept area. No? Okay, because I'm bringing in several things. First of all, you have the correlation. That's pretty close to 1. I would suspect that it has some value, right? And I would suspect that my p-value would be less than some value that's to the right or to the left of my critical values. But it's not telling me the critical values here. It's just telling me a p-value. That means it's really an extreme, almost no area, right? 0 area. And I know that in this area over here, it's accept. Here too. But this is positive, so we're talking about this side, right? So let's go there. Okay, so that's... Okay. Now this is also the correlation coefficient and the linear regression is topics unto themselves, and they have their own chapter. So they're giving you a taste of it here. But before you do that, you have to know this equation. This equation here is the slope of a line. That's why, math, if you have a good algebra, these sort of things are trivial because we're used to dealing with that all the time. Whereas this guy is the slope. That m, okay? That's how steep it is, positive or negative, okay? Let's try one. So that say I have a scatter plot, and it looks like that we have two variables, whatever it is, one y and one x. Now, these are random variables. What does random variable mean? It doesn't mean that the results are totally random. It means you're drawing randomly from a distribution that has a pattern in it. So we're looking for patterns, right? So if we have this scatter plot between the two variables like this, kind of grouped together, then this is a line which we fit in. Let's see. Yeah, this looks cool. Let me try that. Oh, no. Let's try that. Look, we've tried to fit it in. Oh, look. It dotted. Dashed. Wow, that's a thrill. Okay. So, with calculus, we end up fitting this the best fit we can fit. And the way to do it is we minimize, like if you put rubber bands around here with equal elasticity, wherever that comes to rest is kind of like the best fit of putting a line. You understand? That's called a regression. That is a regression. So, this is a positive slope, right? M is greater than 0. Let's see. Right? If it had gone like this, right, the line fit like that, then I would have M negative. Okay? Now, this is a little different than the R, because now, instead of coming up with a calculation R, I'm going to look at this guy right here. I'm going to look at the slope. Okay? When you look at the slope, you ask yourself, if that slope is 0, let's suppose I have a graph where the slope is near 0. If m is equal to 0, what's the equation? Y equals b. True? If m equals 0. If m equals 0, that means 0. That means flat slope. Yes? That's what it means. What does this look like? Well, it's, you got a y-intercept. Let's say that the y-intercept is just some number b. Okay? What does that look like? Well, that looks like this. It's just a horizontal line. What is that telling you? It's telling you that there's no relationship. A flat line doesn't help you do any predicting. So really what we're asking is this slope significantly different than 0? All right, now let's try one. Suppose I have y equals 2x, let's say minus 1, okay? So the way you were to graph that, I know that this thing is a positive slope. So I already know it's going this way. But if I want to graph it, I just do a little small table. I've done thousands of these. And the first thing you ask, well, what happens when x is equal to 0? Well, when x equals 0, what is y? Yeah. Do you see that? Because x is equal to 0, I plug 0 into x. 2 times 0 is 0, minus 1 is minus 1. And then that's called the x-intercept. And then we have this guy, whereas I'm going to call y equals 0, okay? And now I have 2x minus 1. Do you see? So I'm going to add 1 to both sides. Do you see that? 1 equals 2x. And then in order to get the x by itself, I have to divide by 2, right? So in this case, it's a half. Okay, that's just the basic equation of a line. Now, they have things called multiple regressions, where you make the bigger bucks, where it has a lot more variables to help predict. Like I was in called econometrics. In econometrics in graduate school, we put variables together that we thought could help predict how the economy was going to go. So certain models are very accurate, some are just hit and miss. But anyhow, so what would that look like? Well, if you plot this point here, that's 0, minus 1. 0 comma minus 1. And that part here is, let's see, I set y equal to 0, right? Didn't I? So if I set y equal to 0, x is what, half? Is that right? If that's one like that. So it goes something like this. Now, this is y and x. Now, if the slope was equal to 1, you can see that that would be a 45-degree line. So this is a slope of 2. Okay, any questions about this line? Now, they call this y hat because we're fitting it into all these dots. So it becomes a statistics too. Just like R and just like mean, just like the sample statistics. Okay? I don't want to get too much more than that because you're not going to actually fit it, but your StatCrunch can. So let's take a look at that. Let's see if we got this. Okay, so here's an example of regression line. Okay, now this is like y, so this would be something like y equals. Now, be careful because they switch the order. This would be m, right, and this is x, and this is the y-intercept, what we call b. So they just change the order, right? Anyway, I'm most interested in this right here. So that is correlated with this guy. That is M. Right? And that's pretty steep, right? Is that correct? So let's go. Starting to learn. Okay. So there's this. You can make good money with regression, linear regression. So you can see that this fits in there. You know, first you got your correlation coefficient. You see R? That one's 81%, right? And then they give us critical values of this correlation. And then the P, right away, when you see P equals to 0, you know you're in the accept area because it's a lot smaller than the area that would be in the tail of the curve. Okay? And now, look at the linear regression. That's an intercept. The intercept is where it crosses the x-axis over here. Right? And it says it's 80.93, and it probably is. I don't see that. It says B of O is 80.93. Doesn't look right. Anyhow, what I'm really interested in is this guy. Look, this guy. That is the slope, right? They call it B1, so now it's written like y equals B1x plus B sub O. This is B1. B sub 1. Look, compare that to what I just said, y equals mx plus B. All right. See how they just changed the position. They put mx in the back instead of, right? So the slope is B1, right? Which is this. Yes? Okay. Now, how do we judge whether that's, significantly better than, well, we consider that a significant slope? So that's the thing now. That's actually a pretty good reading for a slope. I mean, is it different than 0? It seems pretty significantly different than 0, right? Because 0 would be flat. That means this doesn't predict anything of this. How can this be used as prediction? Well, suppose this carries on this way, right? So that we have 38 or whatever. And we want to make a prediction. We would go like that. Just keep going out. So that we can now say, okay, we think that the next observation will be this much. So you're now becoming a weatherman, a statistician. Okay? Any questions? Uh, huh. Okay. Is that it? Okay, that's it. All right, so let's go back here. All right, and then, what are we talking about here? The p-value and going to linear coefficient, correlation coefficient. Okay, the same thing. I thought we did that. So this is more correlation coefficient. Didn't we do this? I thought we did that. Linear correlation, finish again. Huh? Is it? Huh, I thought I had some linear regression there. Oh, no, it's not. Okay, any questions? The linear regression is just fitting a line, and you're going to look at the slope to see if it's significantly different than 0. If it is, then the data supports that there's a correlation between the two, right? I guess I didn't have any. I did that on purpose, I guess. Any questions on homework? Are you done with this? Everybody done with 2.4? Is that what it is? Or is it? Huh? Oh, okay. You know what? Oh, you're lucky then. Oh, there's no 2.4? Anybody else? Huh. Well, I got it here, but maybe I took it off. Let me see. I don't know. Whoa. Yeah, there's 2.4. Oh, you're lucky. I just went through all that. I think I pulled it off because I didn't want it to confuse you. But anyway.
Yeah, because I had started doing it, and then I did get a little bit confused with the p-value thing.
Okay.
And then when it was asking, like, to find the critical values, I was like, okay, well, which one are they picking? Because they have the little chart.
Right.
With all the different numbers, so I'm like, which one?
Yeah, it's like they have to tell you. It's sort of like caught in between.
Yeah.
So, let's see. Let's see. So, I can't remember what this looks like. Okay, so this is just your standard statistics. So they want to know your median and your mode, right? So you can calculate it. You can well, the median's easy. Just set it up from smaller to biggest, right? Do you want me to do it, or you got that down? Is it okay? Okay. Now the average, you already know x bar, right? How to calculate it, and you can, once you get that, you can find your deviation, right? So, but this makes it a lot easier because we have this little guy here. Now, sometimes if it blocks this thing, you can go online to get this and then copy and paste. And then we go here, the stats. And then I go to summary statistics. And then I've got it in columns, right? Column. Okay, so here's all of them. N, the sample size, the average, the variance. Now, the standard deviation is the square root of the variance. And then we should have the range, the minimum, the percent quartile. Do you remember how to find the quartile? Let's see. All right, well, anyway. Uh-oh, I got to pick one. Okay, so there we go. So the mean is 47. The variance is 843. The standard deviation is 29. The median is the midpoint. And this is the first quartile. And this is the third. Does anybody know what the second quartile is? Huh? Yeah. The actual median is. So let me show you how that's done. Let's see. Okay. So you just line that up. What is that, 3? Is 3 the smallest? I think so. 3, is it? And then what? 6? That's cool. 3, 6. Somebody help out there. 17? 50? That's okay. I can just erase here magically. Okay, what's next?
47.
And then what, 51? Or 51?
52, 53.
And 94? Oh.
74.
77? Does that look right?
74.
It is. So I got 52, 53.
74.
There's a 74? Oh, shoot. All right. Okay. So 74 and finally. And then what? 77? And then we call this guy the outlier. This is way out there. Okay, so I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if I go like this, 1, 2, 3, 4, and 5. Let's see, then I go 1, 2, 3, 4, and 5. 1, 2, 3, 4. No, I got 3, 4, 5. It ends here, right? Well, they would meet here, wouldn't they? Would they? Because I go 5 this way. 1, 2, 3, 4. Oh, 5. Yeah, so it stopped right here. And this one would call them all the way over and stop right here, right? Okay, so now, this is considered your second quartile. And your first quartile, you need these actually to do the box plots. Because when you have the box plot right here, right? Then let's say that's the graph. And these are the whiskers. Which this one would have a whisker of like 94. It'd be like way down here, you see? Because it's an outlier. And the other one maybe not so much, okay? But this one right here is going to be, depends where that hits. That's going to be your median or your second quartile. And this part here is going to be the first quartile. And this is going to be the third. Okay? Notice that I'm not cranking anything through a calculator. That's why we call this non-parametric. I'm just lining the data up and letting it talk for itself. So now I got here. So I got it now. This guy, then I'm going to come in this way. Right? And so do you see that I have my second quartile, my first quartile? It's going to be equal to 17. Do you see I did the same trick? Like a median, but from here. Okay? And that's how we do the box plot. But anyway, that's how we okay, and then it says so there's a median at 51. We must be ready, huh? I can tell people are moving. Is there anything else, or you got to ask me questions? I don't know where you're at. as far as understanding. I can't tell. Sometimes I have a class of just geniuses, so I don't know. Is that it? Are we out of time? Oh man, we could cover a whole field, huh? Okay. Let's go to the next. Same thing. Median, mean, mode, median, mid-range. It's all trivial. These are all trivial. They're too easy. Okay. Well, if you can see what happens if you have to use a calculator, what you have to do. You have to plug in all these values. And that says these are the annual tuitions of 10 most expensive colleges in the country. Top 10 tells us about the population of the tuition. So it says here, let's see, model the data, the mode of the data. You know what the mode is? It's just which one occurs with the highest frequency. So they're saying that 54,000 is 280. The mode of the data set is 5,280. I don't see any 5,200. Oh yeah, there's one. Is there another one? Oh yeah, there's like, okay. So that's the mode. Now, I don't know if anyone's sending your kids to these universities, but you can see it's not cheap, okay? This is tuition. Okay, so we still got to live. Now, luckily, when you go to graduate school, if you get accepted in one of these schools, you're normally given a research assistantship. So you'll work under a professor to help them grade or teach a class. So that's good. But normally, unless you've got exceptionally high grades on your tests, on your SAT, and on your tests like that, then you can see what it's going to cost you to get a 4-year degree on just tuition. And we're talking about, $200,000, right? Now, in my opinion, that's cheap. Because if you go to that school, the students that you're sitting with and the instructor themselves, they're part of what's making the whole planet move. I mean, they work, You're getting in with the people who own the big industry. You're getting with the latest cutting edge professors. And so 200,000, you'll make that in a year. That's a super investment. So what I'm saying, even if you have to borrow it, as long as you plan on finishing, my brother was at least $200,000 in debt. I was maybe under about 100. I don't like it. I mean, I'd rather it be free. But as far as when I look at the investments in my life to see what's paid off, the rate of return on an investment, for me, it's been education. Next has been the housing, right? You buy houses and stuff. But if you tuck around and figure, so $200,000, if it's lent to you, it's not, there's good debt and there's bad debt. Education, I wouldn't be fearful of it. If you're if you're qualified to go to one of these schools academically, but you choose to go to something because you don't want a school loan, you don't want to get credit, I think you're cutting yourself short. Because the rate of return, it's simply an investment. Okay. Anything else? No? Okay. That was fun. Oops. This one. Okay, that was 1 hour.